Hello, good people. Today we are going to be talking about conservation of momentum in collisions. And so I wanted to start by showing you some collisions. Here we have two cards who you will recognize as Dan and Billy. And Billy and Dan are going to have a few collisions here. The first collision that I want to show you, I'm going to have Dan sitting nice and still here on the table. And I'm going to have Billy, and I'm going to launch Billy towards Dan going fast. And I want you to guess what you think is going to happen to Billy and Dan after I send Billy flying towards Dan. Ready? Is that what you thought? Now check this one out. What we're going to do now is I'm going to have Billy going this way, Dan going this way, and I'm going to shove them both towards each other, going ideally approximately the same speed, but we'll see how well I do here. Okay, ready? 3, 2, 1. Gone. Is that what you thought? And now check out this one. For this one, I'm going to send Billy towards Dan, and I'm going to send Billy towards Dan going fast, and Dan towards Billy going slow, ideally if I can do this right. And we'll see what happens here. Are you ready? Here we go. Whoa! Had a little collision here with the wall. One more time. Billy going fast, Dan going slow. Okay. Now, what I'm going to do next is I'm going to flip the two around. Before, I had a plunger in between the two that's spring-loaded. Now, I'm going to have a little magnet in between the two that will cause them to stick together like this once they collide with each other. Now, here's where I'm going to start. I'm going to start similarly. I'm going to have Billy run towards Dan. Dan is going to start still, and I want you to watch what happens. Check it out. And now, after that, I'm going to try to run Billy and Dan towards each other at the same speed, going opposite directions like this, and we're going to see how this goes here. Make a guess in your head about what you think is going to happen. Okay. So here we have a lot of examples of a lot of different types of collisions. And the main idea or the main concept for today is that you actually can probably make some pretty good predictions about what you think will happen in each of these situations because you already have somewhat of a fundamental understanding of the law of conservation of momentum. Even if you can't articulate it, you already know these things. And so today, all that we're going to be doing in our conservation of momentum work with collisions is we're going to be adding language and a deeper understanding to the things that you see every day and the things that you already know to be true. So we'll add on some conceptual understanding, and we'll also add on a little bit of a deeper mathematical understanding as well. And that's what we're talking about today. 1 second, because I am going to pause this video so I can get a little bit resituated here, and then we will start working on some collisions. Here we go. 1 moment, please. Okay, fantastic. We should be all set to go here. So, today we're talking about conservation of momentum in collision type situations. Now, when we're looking at collisions, you have two objects that are interacting with each other, and a collision really just means two objects that are running into each other. That's what a collision is when two objects run into each other. So when we're looking at collision kind of situations, we oftentimes, in most collisions, will have conservation of momentum rules apply depending on how we define our system. Here's the idea. We know that momentum is conserved in situations when there are only internal forces acting on the system. Well, if you define your system to be the two objects that are colliding, and those two objects run into each other, then there's going to be a force between those two objects that collide. And the force between those two objects that collide, well, that's going to be an internal force because it's inside of the system that is the two objects. So, in most collision situations, if you define your system to be those two objects, the force between them will be internal, and so in any sort of collision situation, you're going to have conservation of momentum. There are two types of collisions that we will take a look at today. Your textbook goes in depth about different types of collisions. So it'll talk about elastic collisions and inelastic collisions and perfectly inelastic collisions and collisions that are inelastic but not perfectly inelastic and that kind of thing. We will talk more broadly about collisions than that, and we will talk about two types of collisions. Here are going to be the two types of collisions that we talk about today. We will talk about elastic collisions. Oh no. Okay, there we go. Yay, pen. Elastic collisions and inelastic collisions. When we talk elastic collisions and inelastic collisions, the biggest thing that elastic and inelastic collisions are about is energy. Elastic collisions are collisions in which energy is conserved. And inelastic collisions are collisions in which energy is not conserved. And that really is the defining characteristic between elastic and inelastic collisions, is how energy is conserved or is not conserved in each type of collision. Now, in an elastic collision, we'll start here. In an elastic collision where energy is conserved, you know, because of the law of conservation of energy, that in order for energy to be conserved, you need conservative forces to be acting on the system. Now, quick side note here, this is something that a lot of students get confused, so make sure that you are like super focused and that this super makes sense to you, okay, because this is a huge thing. In order to have conservation of energy, you need to have only conservative forces doing work on the system. And in order to have conservation of momentum, you need to have only internal forces acting on the system. Notice the difference. For conservation of energy, you have only conservative forces. For conservation of momentum, you have only internal forces. And that is a key difference here. You'll remember from our discussion on conservation of energy that a conservative force is a force that is whose work is path independent. It's a force like gravity, or a force like the spring force, or a force like the electromagnetic force. But then non-conservative forces are forces like friction or pushing or pulling or that kind of thing. Here's what that means. In an elastic collision, both elastic and inelastic collisions have these internal forces between the two objects that collide. But in an elastic collision, that internal force is a conservative force. And in an inelastic collision, that internal force, it can be not a conservative force, and it most likely is not a conservative force. It's probably something like a push or a pull or something like that. So in an elastic collision, because you have to have a conservative force, you have to have something between those objects that is a conservative force, something like a spring, or something that has some bounciness to it, because the spring force is conservative. So in an elastic collision, the force between them is conservative, which means there's some sort of springiness between them, which means that in an elastic collision, you have what I like to call a bouncy collision. A bouncy collision. The reason why you have a bouncy collision is because the objects will bounce off of each other because they are being influenced between each other by a conservative force. In an inelastic collision, you have what I like to call a sticky collision. In an elastic collision, the two objects tend to hit and bounce off of each other because that conservative force is probably a bouncy force. But in an inelastic collision, the two objects will run in together, stick together, and then ride off together into the sunset. Last, I asked my students, where's momentum conserved in an elastic collision or an inelastic collision? And they say both, Miss Wilson. Momentum is conserved. Conserves momentum. Momentum is conserved in an elastic collision and in an inelastic collision because both have only internal forces acting on the system. In other words, the force between those two objects that collide into each other. So both elastic and inelastic collisions have internal forces between the objects that collide. An elastic collision, that internal force is a conservative force, so energy is conserved. And it's a bouncy collision because it's a conservative force, which is a bouncy force. And in an inelastic collision, energy is not conserved, so that internal force between them is not a conservative force, and so instead they stick together and ride off into the sunset. That's your overview. Now, in order to remember these, I always like to say, and this, I'm sorry because this is like really truly lame, like I could do way better here, but this is just how I've always remembered them, and so this is what works for me. You can find something else that works for you, but the way that I remember them is that elastic starts with the letter E, and energy also starts with the letter E, and so then I remember that elastic collisions, energy is conserved. And I also think of elastic as something like a rubber band that is bouncy, and so I think elastic collisions are bouncy collisions. Then the way that I remember inelastic collisions, and I'm sorry to do this, I really do apologize, is that I remember from my word within the word that in means not, and so I remember that energy is not conserved, and I remember that it is not an elastic collision, so it is not bouncy, so this is the sticky one. And that's how I remember the difference between the two. At the beginning of this video, you saw a bunch of different types of collisions. The ones where Billy and Dan were facing each other with the plunger between them, that's an elastic collision because they bounce off each other. And the ones where Billy and Dan were facing each other with the magnet between them, that was an inelastic collision because they stick together and ride off into the sunset. Now, I actually want to go back to Billy and Dan here, so I'm going to make this big, and I'm going to swivel on back over to my table, because I want to talk through how momentum is conserved in both elastic and inelastic collisions conceptually. So give me 1 second, I'm going to pause this, I'm going to run over to my table, and then we'll keep on working. 1 sec. Are we good? Are we rolling? We're rolling. Okay, and we're back. So, here we have Billy and Dan. Here's the first situation that I want you to look at. I want you to look at Dan still. And Billy charges towards Dan. Can you talk about how momentum is conserved? Here's what you should say. You should say Billy starts with momentum. Dan starts with no momentum. And then Billy transfers momentum to Dan so that Dan then has momentum and Billy has none. So initially, Billy had momentum, Dan did not. Then Dan has momentum, Billy does not. And the total momentum of the Billy-Dan system stays conserved. Now look at this situation. If I send Billy and Dan towards each other and they bounce off, check it. Let's say that I send them both towards each other. Let's say that they have the same mass and that they have the same speed. If they have the same momentum going towards each other, then you have positive momentum one direction, negative momentum the other direction, and the total momentum is 0. So you start with no momentum and you end with no momentum because then you end up with positive momentum one direction or positive momentum one direction, negative momentum the other direction, and the two cancel out and it's 0. So you end up in either case with no momentum at the beginning and no momentum at the end. Then I have another situation for you. This time, this is not one that we saw earlier, but it's one that I want you to see this time. Here's a set of masses, which I saw place upon Dan, like so. Now, if I place a set of masses upon Dan and then I send Billy towards Dan like this, I want you to watch what happens if Dan starts still and Billy starts moving. Ooh, a few things here. I want you to see how momentum was conserved. First, do you see how Billy starts with all the momentum, Dan starts with none? Then, what happens is, Dan starts to move forward, but much slower than Billy. Why? Because Dan is going to take the momentum from Billy, but Dan has much more mass than Billy does, and so Dan needs to go much slower. And in fact, Dan actually is going so fast that it actually creates a little bit of a backwards force here, and you saw that because it has so much inertia, so you saw that you had a little bit of a backwards force here on Billy, which allows Dan to move forward even just a little bit quicker. So that momentum is conserved because then you have some negative momentum here and some positive momentum here. But the biggest thing that I want you to see here is that if I start off moving fast here, it hits all the mass and Dan moves much slower because he has more mass. Very reminiscent of what we saw last class period. Now, the next thing that I want to show you is I want to show you an inelastic collision. So far, these have all been elastic collisions, because they're all bouncy. Check this one out. I have momentum going this way, momentum going this way. That's positive momentum, negative momentum. As they head towards each other and they collide, well, they had no momentum to start and they have no momentum to end. And so we say that momentum is conserved. You can also see here, if I start Billy going slow and I start Billy going fast this way and Dan still, then now they share the momentum at the end And so because we have more mass when they're together, their final speed is much slower. So you can see that in all of these situations, the amount of momentum that you start with is the amount of momentum that you end with. It just might be in different objects or redistributed between mass and velocity or that kind of thing. Notice also that you do have to pay attention to direction. That is highly, highly important in any kind of conservation of momentum situation. Okay, folks. Next up, we are going to try a little mathematical practice problem. So I am going to pause the video, then I'm going to go back to my desk. I'm going to sit down and I'm going to open up my textbook to page 216. And you should, oh no, just kidding, page 219. And you should probably do the same. Be back with you in a second. Okay, party people, here we go. We are on page 219. This is question number 2. Here's what it says. We got a 16 kilogram canoe that is moving to the left at 12.5 meters per second, and it makes an elastic head-on collision with a raft of 14.0 kilograms that's moving to the right at 16.0 meters per second. After the collision, the raft moves to the left at 14.4 meters per second. Disregard any effects of the water. Part A says find the velocity of the canoe after the collision. Okay, here is where we are going to start. First, I know that this is an elastic collision. First, because the problem told me. But second, because it says that the raft starts by moving to the right and ends moving to the left, which says, hey, these two things bounced off each other. Whenever we do any kind of conservation of momentum problem or any kind of collision, we always, always, always start by drawing a picture of the initial situations and the final situations. I'm going to start by drawing an initial picture of what's going on here. First, you start with, it says that we have a canoe that is moving to the left. So I'm going to draw a canoe here. Oh my. A canoe, and it's moving to the left. Then, it's going to make a collision with a raft. This is going to be my raft here. Sorry, I know it's not the best raft in the world. Not to say that my canoe is the best canoe in the world, but you get the idea. It looks like more of a mattress than a raft, but you get the idea. Okay, so the raft is moving to the right. And now I'm going to write down some of my knowns and unknowns. The problem says that the mass of this canoe is 16.0 kilograms. So I'm going to record that number. And it says that it starts moving to the left at 12.5 meters per second. So I'm going to say that the initial velocity of the canoe is, 12.5 meters per second. Then I look over at the raft, and it says that the raft has a mass. The mass of my raft is 14.0 kilograms. And then it says that the initial velocity of my raft is 16.0 meters per second. Now, before I even draw my final picture, what I'm going to do first is I'm going to define which way I would like to be the positive direction. I'm going to say for today that to the right is the positive direction, but of course you could make any choice that you want here. So I'm going to say that to the right is positive. That means that my raft starts off with a positive velocity of positive 16.0 meters per second, and my canoe starts off with a negative velocity of negative 12.5 meters per second. It is incredibly essential that you define your positives and negatives and that you label them as such. Now, let's talk about our final situation. In our final picture, my initial picture is always before the collision and my final picture is always after the collision. In my final picture after the collision, it says that the raft, which we shall draw now, there's a raft, look it's so rafty, the raftiest raft. Okay. The raft, which somehow shrank a little bit, I guess. It looks like it got a little bit shorter and stouter. The raft is now moving, it says, to the left at 14.4 meters per second. So I'm going to write that the final, oh, that's a W. That is exciting, but not right. That the final velocity of the raft is 14.4 meters per second. And now I check my direction. I said to the right was positive, and this guy's now moving to the left, so that's going to be negative. And it asked me what is the final velocity of the canoe. So I'm going to draw my canoe here. Now, here's the thing is that I actually don't have any information about which direction the canoe is going. Wow, my canoe also shrank. I actually don't have any information about which direction the canoe is going, but you could probably guess if they start moving towards each other and the raft moves ending away, then this canoe is probably also moving away. And the final velocity of the canoe is what I'm looking for. Now that I have my picture set up, I've defined which way is positive, and I have identified all of my knowns and unknowns. I go to next, I'm going to start with conservation of momentum. And I'm going to say, because I only have internal forces acting here, then momentum is conserved and my change in momentum is 0. That means that the amount of momentum that I had at the beginning before the collision is the amount of momentum that I have at the end after the collision. Now, my initial momentum here, I look over to my picture and I say it looks like the raft has some initial momentum and the canoe also has some initial momentum. So the amount of momentum that I start with is the initial momentum of the raft plus the initial momentum of the canoe. And the amount of momentum that I end with, well, the canoe and the raft also both end with some momentum. So the amount of momentum that I end with is the momentum of the raft at the end plus the momentum of the canoe at the end. And now I'm going to plug in M's and V's for all of my momentums. So when I look at the initial momentum of the raft is going to be the mass of the raft times the initial velocity of the raft. Then the initial momentum of the canoe is going to be the mass of the canoe times the initial velocity of the canoe. Over here I have the final momentum of the raft. The final momentum of the raft is going to be the mass of the raft times the final velocity of the raft. And the final momentum of my canoe is going to be the mass of the canoe times the final velocity of my canoe. Next, I'm going to rearrange to solve for what I'm looking for. I'm looking for the final velocity of the canoe. So I'm going to move this guy over to the other side and divide both sides by the mass of the canoe. When I do this, I get that the final velocity of the canoe is the mass of the raft times the initial velocity of the raft. Notice, by the way, that does not look like a very good R. Notice, by the way, that I always keep vector hats on all of my velocities and all of my momentum values because direction does most definitely matter. So I start with this side of the equation. I'm going to swivel this over to the other side so I get minus mr times the final velocity of the raft divided by the total mass of the canoe. The total mass, as if there are parts to it. That was goofy of me to say. And now I'm going to plug in numbers. When I plug in numbers for the mass of the raft, I plug in 14.0 kilograms times the initial velocity of the raft, which is, do plug in with positive and negative signs here, positive 16.0 meters per second. Then I add the mass of the canoe. The mass of the canoe is 16.0 kilograms. And the initial velocity of the canoe, and we are going to run out of space here. The initial velocity of the canoe is negative 12.5 meters per second. And then finally, I subtract the mass of the raft, which is, as we know, 14.0 kilograms. And I multiply that by the final velocity of the raft, which is negative 14.4 meters per second. Ooh, sorry, super tight on space there. Let me get my face out of the way. Classic. Then I'm going to divide all of that by the mass of the canoe, and I know that the mass of the canoe is 16.0 kilograms. Now, I type this into my calculator, and when I do, I start to think critically about the kind of answer that I should get. First, I'm thinking I want to get a positive number because I want to say that the final velocity of my canoe is to the right. So I'm looking for a positive final answer, and ideally, my number shouldn't be anything crazy. Ideally, it should kind of like match up with something that seems like kind of reasonable here, like something that's matching in the general range of these kinds of numbers. And so when I get positive 14.1 meters per second, I'm feeling pretty good about that. And so I report my final answer as 14.1 meters per second to the right. And there it is. And that is part A. Now, let's go ahead and take a look at part B. Wait for it. We can do it. In part B, it asks you to verify your answer by calculating the total kinetic energy before and after the collision. Here's the idea. If this is an elastic collision, then the amount of kinetic energy that we had to start should equal the amount of kinetic energy at the end. So what I'm going to do is I'm going to calculate the initial kinetic energy. And I say the initial kinetic energy, let's go smaller so we can fit it all on here. The initial kinetic energy that when I'm thinking about the situation, I look back at my picture every single time and I say the initial kinetic energy is going to be the kinetic energy of the raft at the beginning plus the kinetic energy of the canoe at the beginning. And when I plug that in, I would have 1/2 times the mass of the raft times the initial speed of the raft squared plus 1/2 times the mass of the canoe times the initial velocity of the canoe squared. Then I can plug in numbers here. So I plug in 1/2 of the mass of the raft. Mass of the raft is, I don't remember, 14.0 kilograms. The initial velocity of the raft is 16.0 meters per second. Square that, plus 1/2 times the mass of the canoe is 16.0 kilograms. And the initial velocity of the canoe is 12.5 meters per second. Notice here that I'm calculating kinetic energies. And so when I calculate kinetic energies, I am not plugging in velocities, I'm plugging in speeds because kinetic energy doesn't have a direction. And so I don't care about the direction of my velocities. When I plug that into my calculator, I get 3.04 times 10 to the third joules. Now I'm going to take a look at my final kinetic energy. If this is an elastic collision, then the amount of kinetic energy that I start with should be the amount of kinetic energy that I end with. When I look at my picture, it looks to me like the raft has some final kinetic energy and the canoe also has some final kinetic energy. I plug in for the kinetic energy of the raft 1/2 mR times the final velocity of the raft squared plus 1/2 mc times the final speed, sorry, I said velocity back here, times the final speed of the canoe squared. And then when I plug in numbers, I get 1/2 times 14.0 kilograms times my final velocity of the raft, I know is 14.4 meters per second squared, plus 1/2 times the mass of my canoe. The mass of my canoe is 16.0 kilograms times the final velocity of my canoe, which is 14.1 meters per second. Now, when you plug in this number, you should plug in not this number. You should plug in an unrounded value from your calculator. And then when you plug it into your calculator, you would get 13.04 times 10 to the third joules. And you say, wow, this number is the same as this number. And if K initial is equal to K final, then energy is conserved. And we do, in fact, have an elastic collision. Let's take a look at another problem. Go ahead and flip with me to page 216. This will be our last problem for today. We're going to do page 216, and here we are going to be looking for, let's change up our color because it's so fun to change our colors. This is page 216, and we are going to take a look at number 2 today. This is another example of an inelastic collision. So far we've done elastic collision. Let's look at an inelastic one. It says, during practice, a student kicks a 0.40 kilogram soccer ball with a velocity of 8.5 meters per second to the south into a 0.15 kilogram bucket laying on its side. The bucket travels with the ball after the collision, and it asks what is the final velocity of the combined mass and what is the decrease in kinetic energy during the collision. Here's where I start. I start, as always, by drawing an initial picture and a final picture. And I say, okay, taking a look at the situation, I start with a soccer ball, and that soccer ball starts by moving south towards a bucket that is lying on its side on the ground. Here's my bucket. That's not a good bucket, but you get the idea. Bucket. Yay. But still not a very good bucket, but you get the idea. There's a soccer ball that's heading towards a bucket. We know that the mass of the soccer ball is 0.40 kilograms, and we know that the initial, I need good subscripts here. The initial velocity of the soccer ball is 8.5 meters per second to the south. Meanwhile, the mass of the bucket, it says, is 0.15 kilograms, and the initial velocity of the bucket is 0 meters per second because it's not moving on the ground. Now, before I do anything else, I like to define my direction. I'm going to say that this way is to the south, which is the positive direction, so that I can call the initial velocity of the soccer ball positive. For our end picture, the soccer ball runs into the bucket and it lands inside of it like this. So now we have a soccer ball in the bucket, and those together, the soccer ball and the bucket, are moving together, and we are looking for the final speed of that soccer ball bucket combo. To do this problem, we start the same way as we start any kind of collision work. We start by saying that momentum is conserved in this collision. That means that the amount of momentum that I had to start is going to equal the amount of momentum that I have at the end. Well, to start, I have momentum from my soccer ball, but I have no momentum from my bucket. So when I start by looking at the momentum at the beginning, I'm not going to include both momentums. I'm only going to include the one that I need to include. And I say, look, the only person who has momentum at the beginning is the soccer ball. And the soccer ball has some initial momentum, but the bucket has none. At the end, I have momentum of this soccer ball bucket thing. They have now become one unit, and together they are sailing off into the sunset. So I'm going to say that at the end, my momentum, my final momentum, is the momentum of the soccer ball and bucket power combo. And now I break these down into masses and velocities. My initial momentum for the soccer ball is going to be the mass of the soccer ball times the initial velocity of the soccer ball. And my momentum at the end, check it out. I'm going to have the mass of this whole thing. Well, the mass of this whole thing would be the mass of the soccer ball plus the mass of the bucket together. And together, those two things are moving at the same speed, v final. Notice, I only have one speed here because they're moving together. So whatever their speed is, it's the same because they're both moving. Now, my next goal is to find v final. So what I'm going to do is I'm going to rearrange to find v final. And when I do, I get the mass of the soccer ball times the initial velocity of the soccer ball divided by the mass of the soccer ball plus the mass of the bucket. When I plug in numbers, I plug in 0.40 kilograms for the mass of the soccer ball times the initial velocity of the soccer ball is positive 8.5 meters per second. I do plug in direction here because we are talking momentum. The mass of the soccer ball is 0.40 kilograms, and the mass of the bucket is 0.15 kilograms. Now I'm looking for a number when I look at my final answer. I'm looking for something that's positive because I think they're both going south at this point. And I'm looking for something that probably has a velocity that is less than the velocity of the soccer ball by itself. See, now that they're moving together, we have conservation of momentum. So we started with less mass, more velocity. We're going to end with more mass because now we have the mass of both of them, but they're probably going to be going slower. So when I type this into my calculator and I get a number like positive 6.2, I'm feeling pretty good about that number because it meets those qualifications that I was looking for. And because it's positive, I say that this is to the south. And in fact, they will both be moving to the south. And there's my final answer. Let's take a look at part B. In part B, it says, what is the decrease in kinetic energy during the collision? If we're looking for the decrease in kinetic energy, well, really what we're looking for is the change in kinetic energy. So I say here that I am going to look for the change in kinetic energy is what I am searching for. Well, a change in kinetic energy, that's going to be how much kinetic energy I end with minus however much kinetic energy I start with. And this is where I look at my picture to see how much kinetic energy do I end with. Well, the kinetic energy that I end with is the kinetic energy of the bucket and the soccer ball combo. So when I plug in 1/2 mv squared, I plug in for my mass, the mass of the soccer ball plus the mass of the bucket. And then when I plug in my v, I plug in the velocity final for both of them, the speed final for both of them squared. Then for my initial kinetic energy for that 1/2 mv squared, I look back at my picture and I say, wait, it's only the soccer ball that's moving. So I just need the mass of the soccer ball times the initial speed of the soccer ball squared. When I plug this into my calculator, or when I plug in numbers, I plug in the mass of the soccer ball plus the mass of the bucket times, and when I plug in my final velocity here, I'm not going to plug in 6.2. I'm going to plug in an unrounded value here. I think in my calculator is something like 6.1818 meters per second. And then I subtract my initial, amount of kinetic energy, which is 1/2 times the mass of the soccer ball times the initial velocity of the soccer ball, which was 8.5 meters per second. Oh, speed. Gosh, I keep saying velocity. You know what I mean, good people. When I plug this into my calculator, I'm imagining that I'm going to be losing kinetic energy, which means K initial is going to be bigger than K final. And so when I get a negative number here, I feel pretty good about that. And I get a negative number of 3.9, and then when I check my units, I say I'm looking at energy here, so I call it 3.9 joules. And that is my final answer. And that is all for today, folks. Today we talked about different types of collisions. We talked about how momentum is conserved in all collisions because of internal forces, but then we talked about how some collisions have conservative forces for their internal forces, those we call elastic collisions, and those collisions do conserve energy. And then we talked about how there are other types of collisions called inelastic collisions where those internal forces are not conservative forces, and those do not conserve energy. And then we did some practice problems where we looked at both. We also looked at some examples with Billy and Dan where we could see how momentum was conserved in each of those scenarios. And that really is all for today, folks. I do hope that you have a wonderful rest of your day, and I will see you all next time. Bye, good people.